while she prepares my PPT, let me introduce myself.
Okay.
My name is Kyun Park from Korea University. I'm taking your part, sorry.
It's okay, please.
Well, who a long time ago got his PhD from Brandeis University in USA, where I learned Hanukkah for the first time. I learned that Christmas is not that much important. But anyway, so that's where I started. And my advisor, Larry Abbott, we worked on gravity and high energy physics. And then he switched his field, and he's now a faculty of biology in, I think, NYU. And I also switched my field to optics, so nobody's doing particle physics anymore. So anyway, so I'm very glad that I am the last speaker, and I will be much less technical so that you can relax and then go home without heavy-headed things. So anyway, the title.
I like your title above, the first cast Yash Binational Symposium. That means there will be a second and a third. Good.
Yes, and I thank Professor Wook-Jun Yoo and who organized all these things. But he has a background of biology, so I have to also satisfy him. He's sitting all day long, learning about this very much involved physics. So I will just mention about small things later. So anyway, so the title is Transport Waves, Perfect Transport Waves. And although we know that light can travel in empty space, but interesting wave dynamics happens when you consider light-matter interactions. So for instance, like electromagnetic or acoustic waves, when they propagate inside medium, then you can see many interesting things, very basic things, reflection, transmission, and so on. But since this workshop is quantum physics, I have to also mention about the change in the role of light and matter. So if you look at the quantum picture of electrons, and there you have matter wave, and this E&M part provides potential, so the role is interchanged. And actually, so I'll talk about both things, waves, E&M, or also matter waves. So I guess the proper title will be Perfect Transport of EM and matter waves. So that's what I'm going to talk about. Okay, so this wave dynamics, if you think about given epsilon and mu or matter fields, then you can just follow Maxwell's equation and solve it. And then so-called forward problem or just the scattering things. So you can calculate scattered waves from the initial conditions. And so this is really cause and effect things. But now if you change your mind and if you say that, okay, I will consider given scattered fields and then ask the question, can I find the matter part, potentials? So the question is, for given E&M scattered waves, can you find any configuration of matters and so on? Well, this is so-called inverse scattering problem in mathematics, and so this is very much studied. And recently, people working on so-called metamaterial or meta-surface physics, they have this kind of jobs doing. So for instance, like where Harry Potter appeared and this invisibility cloaking stuff, there you have an aim that you don't want to have any scattered waves. So waves propagate like just free space wave, and then still you have certain object to consider. So that's so-called, people called transformation optics stuff, and many other similar stuffs have appeared. So I will not explain all these details, but down to all these very nice works, there are always computations. So you use computer to design these metamaterial structures and so on. And it turns out that physicists are not the best group in doing all these things. It's actually most. And so this comes biology. Sorry. Well, this MOS has very dark eye, and it's called MOS eye structures. And this MOS, well, since it's very weak prey, it doesn't want to be disturbed by predators. So it has eyes not shining. So this eye was evolved into such a way that this MOS has very nice non-fabrication capabilities. So if you look at very closely to the surface of this MOS eye, it has like 100 nanometer scale periodic structures, that's so-called MOSI structure. And this MOSI structure removes reflection very efficiently. So there's this biological evolution things. And also it changes its color and its optical illusions and many things MOS can do. And maybe the best thing is debugging things. The first case of debugging was not in software stuff. It was actually in hardware. One MOS was discovered in the troubled hardware systems. And I guess this Naval Research Lab, I guess that's this diagram in Virginia where I visited, they were very proud that they have this history. That's the place where the first debugging was made. So MOS also appears in computational physics. So very clever thing.
Debugging, can you explain in this context?
Debugging?
Yes, in this context of this MOS.
Well, it was the real MOS which was discovered when they debugged the hardware systems, and they found the MOS there.
Oh, thank you.
Okay, so yes, okay, sorry, I wasn't really clear. Okay, so now at this point, let me raise the question. You have, well, very typical wave dynamics, so-called reflection. So if you look at just a picture like this, then can you remove this reflection completely? And now you know that this reflection, light comes from every direction, and the light is white light, so it has all different frequencies and so on. So can you remove this light completely? And that was the question that I had several years back. And my first daughter in high school, sometime back, she wanted to have some science project, so I explained this MOSI structure, and I asked her to do some computations. Well, of course, she didn't do it. But then I was a little ashamed. I asked myself, do I know the question, the answer? I asked, but I was afraid that she was going to ask me, okay, Daddy, what is the answer? So I didn't have any answer. So, and at that point, maybe a few years later, Samsung Foundation, they provided research fund, asking that you just write down one-page proposal, and then you can have some big money. So I said, okay, it's a very good opportunity. So I wrote down this question, but I wasn't able to fill this one page. It was only 2 or 3 sentences. So the rest of it, I used pictures and other things. So anyway, that was very brief research proposal. Yes, yes, I will talk about both things. Oh, now it's not seeing what is behind. Well, you can do that. So it's really perfect transfer, perfect transmission. Okay, so if it's observer, it's perfect black hole, yes. But if it's transparent, I can make it transparent for both cases. So anyway, so the proper question is, can you achieve this perfect wave transfer by any means? And well, since this is a proposal, I didn't care. So if I get money, that's fine. So anyway, I proposed it, and I got money, and then I got worried. Okay, so this various well-known problem, so-called anti-reflection. So you have very fancy eyeglass, and then you can remove reflection. Also, there's solar cells and TV sets and many things you can find, stealth technology and so on. So there are many applications. Historically, it was first studied, I think it's not the first case, but anyway, there are history always says nothing is first. But Lord Rayleigh, 1886, he looked at this tarnished glass, and when the glass becomes tarnished, actually it reflects less. So good quality glass isn't really good for to reduce reflection. So it's not that much transparent. So it should be aged. And now also this we know very well about so this interference things and this anti-reflection using this destructive interference. Another thing which you want to pay attention is actually 6 years before that. That is, graded index can reduce reflection. That's really MOSI structure. So, when light comes from the empty space into the sun, and you pass through this atmosphere where the reflection increases very gradually. So it's really graded index stuff. And Rayleigh also was aware of that. So he solved very special case of refractive index profile and exact solutions. And this is what this paper talks about. So anyway, both side structure can learn from this. And this is interference and also gradual change. And you can combine both. This interference pattern works only for specific angle, instance angles, and wavelengths. But your eyeglass, if it's Carl Zeiss's expensive one, then you have to also cover all white light. So what they do is they just use multi-layer structures and optimized by trial and error things. So if you look at these technical textbooks, so they say that there is no systematic method. And the design of anti-reflection coatings is done by trial and error. So this is computational optimization. So rephrasing all these things, the question is, can you do it without trial and error? Can you have any analytic understanding of these systems? And well, it turns, fortunately, I was able to answer to that question. So that's what I called AR for white light. And then you can really, I have 1 minute left. Sorry, I'm just kidding. So I heard a bell. So if you think about having collection of dipoles located anywhere, and also collection of different frequencies, and you can have, for instance, like some anti-reflection layer, which is like quarter wave thick, the well-known one, and then you can remove some part of it, but not completely things. But now I'll explain what you should do to remove everything. And here is the actually material things which I introduced, will explain, and which I computationally realized. And then if you do so, then you remove, as you see here, all this collection of light sources, and then there is no scattering appearing. So anyway, so that's what I'm going to talk about. Okay, in order to do so, the material property you need is like what Joon said. It's like you want to have some highly non-local materials or spatially dispersive and also temporally dispersive. So this actually is like instance angle and the angle, this frequency thing. So it has to be instance angle dependent and also wavelength dependent. So it's spatially and temporally dispersive materials. So that's the property which I have just drawn. And so if you have a particular layer possessing these properties, then you can remove it. So let me, even though I said that I will be relaxing and less technical, please bear with me that I will just show simple steps of how I reach it to that analytic expressions. So, well, the main message is that I mentioned about inverse scattering, but inverse scattering, if you go to that community, it's not really systematic and analytic expressions. So you have to also solve all these partial differential equations and so on. Now, fortunately, for this sake, if you consider vanishing reflections, then you can have explicit inverse scattering formalism. So that's what I'm going to talk about. So let's just think about a layer which removes all impedance mismatching so that you remove reflection completely. And then to do so, you impose this, well, this situation is axially symmetric. So I will just assume that this uniaxial dielectric medium where this epsilon and mu is only a function of z direction. So it's graded only along the normal directions. But otherwise, I will assume plane wave expressions and so on. So it looks a little bit technical, but please bear with me. The trick you want to use is that if you restrict yourself to TM case or TE case, later you can combine the most general case. You can express in terms of these basic things. And for instance, if you restrict to the TM case, and then this divergence-free equation and so on, this part of Maxwell's equations can be solved in terms of two scalar potentials and also two functions called impedance and admittance functions. But well, this is straightforward calculation, so I will just skip that part. All I want to say is that here is the Maxwell's equation, in this uniaxial situations. And then using these potential functions, you can rephrase this Maxwell's equation into this nonlinear looking Riccati type equations. Well, just mathematical stuff, but please just accept that. And the nice thing here is that this.
Why is it nonlinear?
Oh,
Equations are linear.
okay, Maxwell's equations are linear. Thank you. But if you rewrite this Maxwell's equation in terms of this potential and then y and z functions, here you find you have y square terms. So it's pretty much like Schrödinger equation, which is second order, and then you can reformulate in terms of Riccati type equations, first order Riccati type equation, but that becomes nonlinear. Similar thing happens here. Okay, so now the real magic happens that this y and z function, which was complex functions, so if I split this thing into real and imaginary part, and if I rewrite this nonlinear equation, I can explicitly separate these material parameters. I can write these things explicitly in terms of these y and z functions. So what that tells you is that impedance and admittance functions are nothing but just wave configurations. So you have scattered wave, and then you can calculate these impedance and admittance functions. And out of this initial data, you can just write down epsilon and mu. So the strategy here is that you want to have instant wave and outgoing wave. If you don't have any reflection, they have certain properties. And then just choose such thing. And then use this particular formula. And then you can have epsilon and mu explicitly out of this. And this epsilon and mu will give you what you wanted. So this is on-demand stuff. So for instance, I wanted to have complete removal of reflections. So that means I have the configuration of this instant incoming wave, y1 and y2. So this is initial conditions. And if I don't have any reflection, then this boundary condition is the if and only if conditions. So if you have y and z functions satisfying this boundary condition, and then any function satisfying these boundary conditions through this relation can realize complete removal of reflections.
For example, it may happen that mu would become negative, or epsilon would become, I don't know, less than 1, or
that,
some such.
yes, there's some parameter range. It can happen, but also you can avoid it. So, for instance, like if I have some constant and epsilon and mu, so you can have many solutions. Actually, infinitely many solutions are possible. So this is one particular solution, and yeah, answering to your question actually, here if you look at it, I have chosen these parameters cleverly so that I can avoid this negative part and so on. So you can have some parameter range to realize these things. So anyway, this is the epsilon and the mu configurations and solving all these boundary conditions. So, okay, so applying that epsilon and the mu, you directly calculate this reflection coefficients and so on. And this is the reflectance, which shows you TE, TM-like, and also there is a Brewster angle here, and also angle, the frequency dependence happens, so that it works at specific angle and instance angles here. But now, if you apply that solution, then you can just remove it completely. So, all set. So it works. And now I can just, to simulate things, I can have one dipole here, and then it diverges and it enters at every angle. So that usually it shows some scatterings depending on the instance angles here. But if I apply that specific dispersion, then I can remove it completely. So it works. Now the big question is, here I introduced epsilon and mu, which is spatially and temporally dispersive. Is it real? I mean, you can ask, can you make it? And that's the big question. Well, if it's just hypothetical, like you said, that if you cannot really have your physical systems to realize that, that doesn't really mean anything. So fortunately, this property required was the K and omega dependence thing, so it's really spatial and temporal dispersion things. Well, what that means is that it's non-local in space, like you said, and also non-local in time. So it's dispersive in that regard. So, but nice thing here is that metamaterials, and actually all atoms and these structures which have some inhomogeneity at microscopic level, they depend on K. So it's essentially they're all dispersive. It's only after you look at the meta scales, the wavelengths like few hundred nanometers, then they homogenize, and then you don't see these fine details of this inhomogeneity. So then you don't care about these dispersive things. But otherwise, if you make those inhomogeneity structure or inhomogeneous structures scale of lambda, like quarter wavelengths and so on, then you can see these dispersive things explicitly. So anyway, that's the thing I noted. So for instance, this is just one example I have drawn. So if you make a structure like some diamond layer structures like this, so multi-layered, and then you can effectively simulate or realize this dispersion, the dispersive behavior. So here I have shown you with this particular structure, this wavelengths covering white light and also this instance angles up to about 80 degrees, you can remove reflection down below 1% and so on. So that's really possible. Now, to really demonstrate experimentally, I used microwave experiment. And then here I have, very nice, my student, they created all these structure samples and then they measured. And here, as you see, you can really remove, within some particular frequency band, you can remove reflection completely. So almost achieving 100% transmissions. So that's possible. So that's the first part of my talk, and I will go very quickly the second part. Now, here I only talked about flat interface and adding one layer with uniaxial symmetries and so on. But you can go beyond that. Like you can think about curved surface like lens surface or any other curved surface. And there you can use so-called transmission optics properties. Well, what that means is that if you think about keeping the equation fixed and then changing the coordinate, and then you usually find you move from one solution to another solution. So that's seeking for symmetry of solutions. So there you have some Lie group structures and Lie group symmetries and so on. But sometimes you go beyond that, like take the coordinate transformations and the equation can change. But sometimes that change the equation, you just, you change part, you just push that into some epsilon and the mu things. So that's what they call this transformation optics. So I'll not go any further details. Here, if you change coordinate and this transform part, you simply call this another new permittivity and permeability tensors. So that strategy you can adopt. And the previous index matching scheme, and then I combine that with this transformation optics, and then you can make curved surface anti-reflection. That's possible. And what's more interesting is that more recently, the paper is in preparation, but here, total internal reflection, which is unavoidable usually, you can combine this concept with transformation optics and so on, and also you can remove. This is the high index part entering some low index things. So depending on instance angles, they got completely reflected. So this total internal reflection, whatever you do, they always reflect. Even though you put some anti-reflection layer, it doesn't matter. Because of this transverse momentum matching, you can say that it always reflects. But now if you apply this transformation optics with what I said before, then you can show that this total internal reflection can be removed also completely. And I can extend this to the acoustic theory. So the change here is epsilon and the mu change to bulk modulus and what? Bulk modulus and rho mass density. So you can also find some analogy to that, and you can extend this to acoustics. So that's also possible. And more interestingly, as I said, quantum physics. You look at the meta wave, and you can also transform Schrödinger equation into this fashion, like some Riccati type. and you can apply this inverse scattering scheme there. That also works. So what this tells you is that here, electron wave entering some potential steps or potential barrier by applying certain specific configuration of potential and effective mass, then you can remove the reflection of matter waves of electrons. So electron can penetrate this potential without any reflection. That's also possible. Oh, this plus, sorry, this is my student. This is the source position here, and this is instance angles. And there is no reflection. It just passes into this in between. This is the potential region. So in front of this potential region, you apply certain layer, the layered potentials, and then you can just, push these all electrons enter into this region. And for the practical side, I can apply this to the waveguide stuff. And for instance, like optical fiber, if you combine this to silicon waveguide of order of 400 nanometers and so on, this is like several tens of microns. And this huge mismatch of size makes impedance mismatch very huge. And so because of that, real applications, they use some taper structure, which is very long. So that's not really practical. And here I can also apply this, this technique and make this very thin. And here is just one particular structure I have built. And so if you apply that, well, this microwave demonstration shows that you can also remove this joint mismatch, very nicely. So this also good. This is good for waveguide structures. And another application I made recently is with my colleague in EE department. And these photo detectors using pin diode structures, you can also increase the absorption rate very nicely. So we double the efficiency of these photo detectors using this technology. So it doesn't really take much effort. You use silicon and SiO2, amorphous silicons and SiO2 structures, multi-layered, and you can achieve, well, not completely perfect, but you can achieve very nicely. So let me just summarize. Here I introduced the principle of what I call universal impedance matching. So the main message was that you apply, or you just employ spatial and temporal dispersions in appropriate way, and then you can have this explicit inverse scattering, and then you can have any functionality you want. So removing reflection is just one particular example, and actually you can design other cases, and you can also have some design principles for that. And more interesting stuff is probably the last part, quantum physics. You can also control matter waves by controlling potentials or some effective mass. I don't know how to realize that, but making them some sort of non-local, like you said, and some superstructures, maybe we can control electrons in a better way. So more to come. Thank you.
Okay, now the session opens for the questions. So we have plenty of time. So if you have a question, Jeon, please.
Yeah. So I think we are doing very similar work in terms of non-locality. Yeah, in terms of non-locality. So for example, if you solve the Maxwell equations in Weyl systems, you have magneto-electron coupling depending on position as well. So the E, mu depends on position. So in that case, probably you have something like anti-reflections in Weyl systems. Those kind of studies already done, or I'm very curious about that.
I don't think so, no.
Is there any reason? Because as you mentioned, the E and mu is dispersive or depending on the coordinate, something like that, then you have this kind of interesting phenomena. Then I think the Weyl system also have those kind of properties. E mu is non-local or dispersive as well. So
I think this is very interesting.
You see this kind of physics.
Yes, this is very interesting. You mentioned about E and H being parallel, and then having some chiral current and so on. So E and H or B becomes parallel if it has very strong diffractions. So these nanostructures can create such environment. And also this nanostructure can create some non-locality in terms of this electromagnetic fields. And that when combined with your electron systems, that's a very new area to think about.
Yeah. So artificial photonic crystal mimic the kinds of topological system as well, and also while is 3D, which modifies the mu and E as function of position. I think you should
Position
try.
and K, both.
Yeah. I think so. Yeah.
I have a question about the electrons that you say going through a barrier. So suppose the barrier is a kilometer wide. You say that the electron will go through this kilometer wide, tunnel through in vacuum and go to the other side? Hard for me to believe.
It's very much like flat band, analytically zero things. So I think theoretically it's possible, but it has exponentially small. So you have to wait quite long building of time. And so what I have shown you, I firstly assumed on monochromatic, single omega dependent things. So that takes infinite amount of time, like you said. But if you send electron and just turning on things, electron, one electron goes, and then maybe it takes the age of universe, to really get the penetration if it's kilometer long. So it's really uncertainty principles involved.
Can I volunteer
yes.
another response? You see, one way to get out of a prism, if you have a quantum particle, which is monochromatic, and the prism walls are in one dimension, is to build a second wall. Right, and then you have also antenna. So even if it is a kilometer wide, build another kilometer wide, and then cause an antenna, and then go.
Yeah, it's a single element.
Yes, it's monochromatic.
But here there is.
I don't know about how you
Mm. Oh, that part. Yeah, the microwave experiment. Well, maybe this is probably what you are saying. Yeah, here I apply this UIM on both sides. So it doesn't matter, this reddish region, how far, how thick that is. You can have the instant and outgoing part all, transparent. So like you said, if you have another layer of this, then it works.
So in standard optics, we can make like broadband anti-reflection coatings that work pretty well over a wide wavelength range and over a rather wide angle of approach. So where is the difference? I mean, how low can you go in that sense?
That's a very good question. Yes, actually, it is real scaling problems. Like if you think about layer thickness several times of wavelengths, for instance, simple grading would do the job for very broadband range. So like you said, you can have some multi-layer structures gradually increasing, but if it's thick enough, then you can cover, all white light part and so on. So the real question is that if you want to have like, very thin layer which can do the job, that requires highly dispersive behavior, like what I have said before, and also the real practical applications. They don't really use, the gradually increasing or decreasing index things. They use alternating high contrast, combinations, and you don't really understand why that happens. But if you adopt this formalism, and then you can, for instance, like you can have some multi-layer structures with different high-low directory index. They form kind of photonic crystal structures, and that gives a band. And this band folding gives you proper dispersion relations, which is actually anomalous dispersion. So it provides some underlying, mechanisms how it works. So it really thickness things.
It's good to know that we can find a solution for the universal impedance matching layer, but my question is that do we have an universal method or fabrication for what we want to make?
That's a very good question. So here I was only imitate, like here is a double layer and triple layers, and then again it's again optimization problems. So like you said, is there any universal, fabrication, systematic way of saying that using only homogeneous materials, but like layered structures? And I'm working on it, and answer is almost positive. So, but I cannot say it directly right now. It's still working.
Professor Avron, do you have a question?
I have a remark. I think it was Schrödinger who realized, if one does one body quantum mechanics, then quantum mechanics looks a lot like wave mechanics. But I think it was Schrödinger who realized that the essence of quantum mechanics is that the wave equation is not in physical space. Mm-hmm. The wave equation of if you have more than one particle occurs in a phase space, in a space which is not 3 dimensions, it's 6 dimensional, depending on how many particles you have. So this is the hallmark of quantum mechanics, and this is what makes quantum particles' behavior different from just ordinary wave mechanics. So I think it might be an interesting challenge to do this with more than one particle.
I see.
Any other questions? If you don't, maybe I can ask one question. So, so you show this anti-diffraction plot, and I think I can imagine that this non-local in space is easily manipulated in real experiment, but the temporal part is, I think, would be more difficult. Or I just want to ask you how this temporal non-localness is important in your formulation.
Well, actually, you can find many materials which are already temporally dispersive. All materials are actually temporally dispersive.
Sure, but okay.
But I understand
yeah, sure.
your part. So if you combine, these inhomogeneous layered structures, they also induce temporal dispersions. Mm. So you can also manage that. Mm. So it works both.
Okay. Okay, so if you do not have any questions, so let's thank our speaker again.